Okay, hi. So, let's start off with the solution. So, exercise 9, question 6. So not all of it, part of it. So, please make sure you don't make any copying mistakes, because this might change your results considerably. So make sure you copied it correctly. And you didn't find basis for all three subspaces U, V, and the intersection of U and V, just U and the intersection. Okay.
Did you just say just U and the intersection?
Right. In the original question, you were supposed to find basis for U, V, and the intersection of U and V. So here, just find basis for U and the intersection. You didn't look for a basis for the intersection. Or, well,
How can I do that without reading? Yeah.
it's okay to find on your way, but this is not part of the solution, and basically I think you can do it even without looking for finding specifically a basis for V, but you don't have to present a basis for V, basically.
What's the name in English of the 100, 011, 001?
When with the elementary basis?
Elementary basis?
Right.
Okay.
Standard basis, sorry.
Standard.
Okay, so now. So till 11 questions. Please explain what you're doing, okay? Especially if you're using, as I recommended in the question, coordinate vectors. So explain what you're doing, how do you get to it, because this is, I don't want to see just the technical part, because this is important but not the main thing. I want to know how did you get to whatever technicalities you're using. That's the main issue. don't go outside, stay in. Just call everyone in. Anyone else? Steve?
nothing better.
בשבוע שעבר השארתי ז'קט בכיתה, ומישהו לקח לי אותו. ואני יודעת כי הייתי פשוט לקחתי ז'קט של מישהו אחר. אז הודעתי כבר בחלק
אוקיי,
שלי,
רגע.
יאללה, אני רוצה לחזור לזה.
אוקיי.
כן? אבל מה זה לא ז'קט הרי?
למה לקחת את הז'קט? מישהו מתחיל להסתובב איתך לו עכשיו.
לא, הוא לקח את הז'קט שלי, אני החזרתי את הז'קט האחר, אבל לא החזיר לי את שלי.
למה? זה פשוט שלך.
אוקיי.
אני יכולה להסתדר עם הגדול.
מה?
יכולה להסתדר עם הגדול שלי. מה הוא יעשה? אף אחד פה לא יגיד לו כלום.
אוקיי.
ז'קט מאוד עקום. מאוד עקום.
So the first thing we have to discuss is purely technical. Next week, on Wednesday, the class is planned to take place in another room. This, I guess you already know. Now, I want to. This happens because here there is some event from 10 to 12. And our class begins at 11. So I want to check with you one of two options. Either to shift the class so it begins at 12 and ends at 3. Alternatively, to have next week only 2 hours and then the next week have 4 hours.
What is the event?
What?
What is the event?
Here.
No, what?
That's why we are evacuated. What is the event? Inauguration of a Max Planck program between Hebrew and Max Planck
Why
Berlin.
can't we just do 3 hours next week?
What?
Why don't we just do 3 hours next week?
3 hours, but then they have to be shifted from 12 to 3.
If the other room is shifted?
No, the other room will take care for that. Don't care about the other room. Maybe they'll change the room again, but
We can do it in the normal hours in another room.
Right.
what?
We can do it in the normal hours in another room.
We can no. The problem is that I have to attend the 10 to 12 event. Okay, that's the thing. So either 12 to 2 and then next week 4 hours, or 12 to 3. 12 to 3. Who votes for 12 to 3? And who is against 12 to 3? A few. So I'll check the formalities if I can do it, even though 2 of you oppose, and I'll take a final decision, and I'll notify you by mail. Okay. So now with the real real stuff. Okay.
If it will be next week 2 hours and then 4 hours, it will be again 1 hour.
No, it will be 10 to 2. Because I understand the hour between 10 and 11 is less problematic than 2 to 3.
It's better 10 to 2.
What? It's better 10 to 2?
Better earlier than late.
Yeah, of course. But so,
Just only
is there anyone with a real problem of having next week 4 hours, or you just don't want to have to suffer 4 hours? Okay.
We can start an hour early.
Let's do it offline. What?
We can start an hour earlier in the other room, in another room, or that room is free, the small room.
Forget the room. The room is not an issue.
No,
Okay.
I'm saying the next
Next week.
Not the next week, the week after next.
Okay, the week after that.
So we add the extra hour.
We had extra hour before. 2 to 2 we'll have.
אבל החדר הזה תפוס בשעה שזה...
Don't care about the room. It's no problem. The room is no problem. Okay.
אין problem, קיצור.
Okay, that's something. This is technical thing we can settle. So, is there anyone with real classroom prior to this room? So I think it's more reasonable to set it for next week 2 hours and next week 4 hours. Okay? I'll manage. You'll manage. We'll go through this together. Okay? You'll have a shorter exercise.
אוי, זה לא...
If you have only 2 hours. Okay.
Okay, so this will be settled most likely. Okay. So we've discussed linear transformations. These are objects, functions t from between two linear spaces, such that they are they respect they respect the linear combinations in the spaces. So t of alpha v1 plus beta v2 is alpha t v1 plus beta t v2. Okay, this is the condition. Now think about the collection of linear transformations between two given spaces. So now we're thinking about the set of all linear transformations between two given spaces. So we have all the objects T such that T is between two given spaces. Okay, T from V to W is a linear transformation. Okay, but remember, V and W are fixed. It's not that I take all linear transformations in the world. It's just V and W are fixed, and I think of all the linear transformations between these spaces. So this is called the set of homomorphisms from V to W. This is not very important. I just want to say something about linear transformations. Yeah. And any other linear transformation you can think of between 2 by 2 matrices, for instance, and scalars. Okay. For instance, okay, just you take all of them, all right? You take all of them. It's easy. Okay, so think of from R to R. Okay, this is easy to visualize. What is the linear transformation from R to R? Okay, again, a linear transformation is in particular a function. So you can think of a function. What are? Let's think of the graph of the function. What are the linear transformations from R to R? Are these all linear functions?
No.
What requirement should be there? Why not?
It should be, you shouldn't have any parts that are not defined.
No, I mean linear transformation, like linear function from R to R, like a line, linear function. All of them are linear transformation. Linear. There's the difference between linear transformation and a linear function. Linear function is indeed anything you can draw, you can sketch a line. But what is the linear transformation? What requirement should be? Yeah, it should go to the origin because 0 has to go to 0. Otherwise, it's not a linear transformation. Okay, so all linear functions that go to the origin are linear transformations. So this set of functions from R to R is the set HOM RR. Is the set of all linear transformations from R to R. Okay, all line functions that go through the origin this is hom RR. Right? So now we can think of, okay, now this is a very complex concept. We have a set of functions, and now we can define operations on these functions. What do I mean by operations on these functions? We can add two transformations together, and we can multiply a function by a scalar. We can define a addition, a summation, and multiplication by a scalar on the set hom VW. Okay, as follows. How can we add two transformations together? What would be a natural way to sum two transformations? So suppose T1 or T and S. T and S are from V to W are linear transformations. So now define T plus S from V to W. Okay. Define T plus S from V to W by, if I want to define a function, I should say, where does this function send each element of V? So, T plus S of V, what is it going to be? TV plus SV. TV plus SV. Now, note, this is a new summation rule, a new plus sign. It's the same plus symbol, but it defines a new operation between two linear transformations. This is summation where? In W, right. T plus SV, TV plus SV, and now, and for some lambda in R, define a new function. For now, it's just a function. I don't know if it's a linear transformation. We take two linear transformations, we define a new function, and then we take one linear transformation and one scalar and define a new function, call it lambda t, from V to W, by what would be, if we want to define a new function, we have to state where does it send each element from V. Where does lambda t send V? We send it to lambda t of V. So again, this is a new, this is all concatenations, but you have to understand what is hidden here. So this is multiplication, new multiplication rule. This is not multiplication. This is just plugging in the argument V into this new function. And here, this is multiplication in W, and this is plugging in the argument V into the function T, right? So no notation and no symbols, but it says different things, right? In case, well, if T is, for instance, the example of a transformation related to a matrix, I remind you that we can take a matrix and then define the transformation by matrix multiplication. This will be indeed a matrix multiplication, but this is the general case.
Question?
Yeah.
So both are initially defined as functions, not as linear transformations.
We don't know anything now yet about T plus S and about lambda T, right? And indeed, it happens that the result, T plus S, the new function, T plus S, and the new function lambda T are linear transformations. the new functions t plus s and lambda t are linear transformations themselves. So let's prove it for t plus s. How do we define that? How do we prove that t plus s is a linear transformation again from V to W? Linear transformations from V to W.
Take two vectors in V. And then
Right.
show that
Take V1, V2 in V, and what else is advisable to take? Yeah, what? Two scalars, yeah. And alpha 1, alpha 2 in R. And now what do we have to show? In order to show that this is a linear transformation, yeah, we want to show that t plus s of the combination is the combination of applying t plus s. Now, t plus s on this linear combination, alpha 1 v1 plus alpha 2 v2. Now, first we go by the definition. What is t plus s? What does it do to a vector? It takes t of the vector plus s of the vector. It's t of alpha 1 v1 plus alpha 2 v2 plus s of alpha 1 v1 plus alpha 2 v2. And now,
we're dummy TNS.
since this is by definition of t plus s, this is by definition of t plus s. Now, since t and s separately are linear transformations, since t and s are linear transformations, this is equal to alpha 1 t v1 plus alpha 2 t v2 plus alpha 1 s v1 plus alpha 2 s v2. Now, we apply, let's do it slowly. Let's apply commutativity in W and distributivity in W. Applying commutativity and distributivity in W, we get, so let's put them together, it's alpha 1 TV1 plus SV1 plus alpha 2 TV2 plus SV2. And now,
You can put alpha inside.
no,
And
no, alpha, we want to stay, remember, we want to alpha to stay outside. We want it to be alpha 1 T plus S V1 plus alpha 2 T plus S V2.
no, you want to show that this is equal T alpha 1 v1 plus alpha 2 v2 plus S alpha 1 v1 plus alpha 2 v2.
No, this we know already.
No, so
We want to go back again to the new transformation. We want it to be alpha 1 T plus S of V1 plus alpha 2 T plus S of V2. So this is evident from here, but what exactly we apply when we go? The definition of T plus S. Yeah. By definition of T plus S. So here we use the definition one way to separate the T and the S. Here we use the definition to put them back together. TV1 plus SV1 is by definition T plus S of V1 is alpha 1 T plus S of V1 plus alpha 2 T plus S of V2. And now observe if anything you lost because it was rather quick, just observe the beginning and the end. Go at home on the middle part, on the argument. So this shows that T plus S is a linear transformation. This shows that T plus S is a linear transformation. And the same is true for lambda T, right? Similar proof. Right. Lambda T of alpha V1 and plus alpha V2 is alpha V1 lambda T of V plus alpha V2 plus alpha 2 lambda T of V1. Maybe I mixed it when saying. Again, go to the definition. So what is established by that? We've defined a new set, home VW, and we've defined new operations on this set, and these operations we've shown are closed. It means that if T and S are in home VW, T plus S, this new definition of summation, T plus S is in home VW, and lambda T is in home VW. So what does it make home VW? Is it? So quick? Well, first of all, now it's a candidate to be a linear space, right? Because this is something new. This is not a subspace of anything we know. This is something new. It's a new set, new definitions. If we want it to be if we want to know it is a linear space, we have to go through all the requirements for a set with two operations to be linear space. But this can be done fairly easily and straightforward manner. And so this makes home VW along with the two operations a candidate for a linear space. We've just shown closeness. Of the operation, under the operations, the linear operations. It remains to show everything else. Now, you practically have all that it needs. I gave you an example of the zero transformation. This is going to be the zero element, and but you have to show that it's indeed acts as a zero element in home VW, and so on and so forth. Maybe it'll be in the exercise, maybe not. I'll think about it. Okay. But indeed, is straightforward. Lot of work, but straightforward. To show that home VW is a linear space. So any questions till now? So one thing we're going to do next class, and I'll give you the start point of it now before the break, is presumably we can think that home VW is something huge. It's something that we can't even grasp. All the linear transformations between two linear spaces. It's quite a lot. As you try to give an example of what is inside some home of two linear spaces. Yeah, so there are a few examples, but in fact, in some cases, and then you can think about it in all cases, this is in fact something you already know. Like it's something you can already grasp what is home VW for some of the V's and some of the W's. So I'll just state the theorem we're going to prove, and so what are the consequences and what is the meaning of it, and then we'll shortly prove it in the next, after the break. So, so now I'll state a theorem, and we'll sketch the conclusion from this. So, let V be, yeah, okay. Let V, can, let V be, no, not specific name. Let V be Rm and W be Rn. Just a moment. Let V be Rn and W Rm. If T from V to W is a linear transformation, then there exists a unique matrix A in space of m by n matrices such that, give me a guess, what's going to happen?
AV equals W.
That AV equals W. I want to say something about T. T is TA. You remember what is TA? TA, I gave you an example and said this is going to be an important example. And I told you, given a matrix A, define the transformation TA. What does it do? It just acts as multiplication by this matrix. Recall that for matrix A, TA of V is AV. This is the transformation of matrix multiplication related to the matrix A. So what does this theorem state? The theorem states that any transformation between V and W can be represented by a matrix multiplication. Okay? Any linear, what we've shown earlier is that for any matrix there is a corresponding transformation. That's reasonable. But now we show the other way around, that any transformation can be represented by some matrix. Okay? So what would be the conclusion about home Rn Rm? What does this theorem say about home Rn Rm?
Set of matrices.
right, that it corresponds in a way, it's not that it is, but it corresponds in a way to the set of matrices. So, as I told you, Hom, Rn, Rm is something you already know. It's, in a way, all m by n matrices. It corresponds to all m by n matrices. Okay. This, the what?
All n by n, there's no group of n by n matrices are not equal.
As we said, we said last time that every matrix you can set a linear transformation. And now we said for every linear transformation you have a matrix. So this gives you a one-to-one correspondence between these two spaces. Okay. The conclusion is that there is a one-to-one correspondence between Hom Rn Rm and the set of matrices, m by n matrices over R. Okay, so let's go for a break, and in 10 minutes we'll start the proof, and in hopefully 12 minutes we'll finish it. כן, אני עניתי לך הבוקר שזה כן כבר מאוחר מדי, אבל הצעתי שניפגש מחר.
בבוקר, יש לי שיעור מ-1 עד 5.
הצעתי ב-11:30. אוקיי, אז תענה לי למייל ו...
זה לוקח הרבה זמן, נכון?
רגע, הנה בוא תפתח. I don't have your full submissions returned yet. Sorry, but I couldn't complete all of them, so...
You released the solutions for exercise 8.
Um,
Someone still has to present it?
yeah, I will.
Okay, great. Thanks.
אתם עבדתם יחד, נכון? על התרגיל הזה. היה לכם את אותה טעות מאוד יסודית. זה היה ממש נראה... חשבתי שאולי עבדתם יחד. אז לשניכם היה את אותה טעות יסודית, לפחות לדבר אחת עם שנייה על הטעות. כן, זה לא אסון, לא לבית. לא קרה כלום. כלומר, עוד פעם? רגע, אדר? אבל... אבל אתה יכול שנשארת את זה שם וזה נלקח... שאלת את רותי? אולי מישהו? ולא הגיע אליהם. לא תלוי פה. אוקיי. טוב, אני מניח שבסוף הסמסטר תוכלי להכריז עליו כשלך. אבל כנראה גם מה שלקחת היה לא של מישהו מהכיתה, אלא... אבל יודעת, יש סטודנטים שבכלל לא באו היום, נכון? מתן לא פה היום, ונמרוד היה רק לרגע, ו... אוקיי? אני אשלוח לו מייל. צריך לשלוח מייל לכל רשימת קבוצה, יש לך את הרשימת קבוצה. שומעים אותי שם? לא, באמת, עכשיו שומעים אותי? אוקיי? שומעים אותי במיקרופון עכשיו? אז מה זה האדום הזה?
Then I said that I did something like that.
But the key question is, how do you do it without finding V, without finding the
finding?
base of V, right?
Oh, you don't have to find. Oh.
Yeah.
Well,
That's why I was like, I knew that it was also two-dimensional, but like it kind of confused me, thinking like if you had no idea what V
two-dimensional. It's just, a fairly simple operation.
No, I know. I'm saying,
Oh.
assuming you don't know.
Oh, okay. So
Assuming you don't know anything about me,
I guess
would it be possible?
that doing this method, you can also discover the same thing without using the fact that V is two-dimensional. Only it will be more work. So I did it like this. Well, I saw I had alpha. I invent.
Yeah. Okay, and then
And
that's
then
equal. Right.
and then you see you solve it, and you get alpha equals gamma. No, alpha equals delta, beta equals gamma, and alpha equals minus 2 beta. So what does it mean? That it means that every vector that satisfies both this and this could be represented as minus 2 beta times this plus beta times this.
Right.
And this gives you only one vector. This gives you a linear space with base 1.
Okay.
So I guess this is the,
Yeah,
if I'm not
makes sense.
mistaken, this is the answer.
Okay. I guess something like that.
Yeah.
I'll get a 1. That's interesting.
Yeah, in the beginning I thought the intersection would be also dimension 2, but no, it's
Okay, that makes sense. Because you set it equal. Because the key is there's some linear transformation that. How do you to get the equation in the first place?
yeah.
It's
So
because
I just said, I think that's the only weak part of my. I just wrote. I had no time, so I wrote. Okay, we can represent the same vector in C3x, the same vector in another base, and this is just taking its coordinates according to
and
the standard
multiplying it
base.
by some other.
Yeah.
Right.
So every time I could go, go back to the original base.
It's so much easier for me to understand these things on a line. So you have a line, right? And so so you can express this point if you just multiply it by some alpha and beta, and it's still in the same line.
Yeah.
That's the idea. So much more obvious to me like that.
שלחתי SMS ליואב,
I went over last class
What?
night.
What?
Last class, I
Yeah.
went over the notes last night, and I was reading. I was during class, I had no idea what was going on, but it was actually pretty easy.
Yeah. I think the main issue with linear algebra is getting familiarized with the terms. So in the second it comes natural for you, then it's good.
Today was not too bad.
לך נתתי נכון?
I think what I should have done is maybe studying that during the holidays. I could use the summer and work time, and I think then
כל הצירופים הליניאריים,
if you've gone through it once, and
כל
a lot
הצירופים
easier
הליניאריים
to
של הוקטורים ב-A.
Okay.
כלומר, ספן
אלפא
של V1, V2,
Third time, fourth time.
זה אפשר להגיד, זה כל הוקטורים מהצורה אלפא 1, V1, ועוד אלפא 2, V2,
The more I listen to this.
ואלפא 1 זה לוקח את כל הצירופים, אפשר להגיד אלפא 1, אלפא 2 ו-4. כל הצירופים הליניאריים.
אתה לא משווה את זה למשהו מסוים. רק...
לא, כל הצירופים הליניאריים. זה מה שחשבת.
כל הזמן חשבתי שצריך להשוות את זה לאפס או...
לא, אתה לוקח את כל הקומבינציות. נגיד, ספן של 1, 0, 0, 1.
זה 1, 1 כפול...
לא, זה לא 1, 1 כפול, זה בעצם כל משהו מהצורה A, B. כל הוקטורים A, B, אתה יכול לקבל. זה בעצם R2. R2 זה כל הזוגות. זה ספן של 1, 0, 0, 1.
שיש לי...
רגע, בואי נעשה את זה או בהפסקה הבאה או כי אנחנו צריכים להתחיל, בסדר? אוקיי. אוקיי. All right. So this is what we want to show. We want to take a linear transformation and assign to it a matrix that does the same thing by multiplication. Okay. So woof. Okay. So let A be the following matrix. So I'm going to describe it column-wise. Right. So the first column is going to be T of E1. I remind you, E1, EI is the ith element in the standard basis. Is this vector with all zeros, and in the ith position, there's 1.
What does TEI mean?
Just a minute, ith position. So we took a linear transformation T from V to W, right? So V in particular is, this is Rn, and this is Rm, right? So I'm taking the standard basis of Rn. This is E1, E2, and so on. I have n such vectors in the standard basis. So TE1 is going to be the first column. So how many rows are in this matrix? Right, TE1 is in Rm. Therefore, there are m rows in the matrix. And the second column is going to be TE2. Apply the transformation to E2. Ask yourself, where does T send the vector, send the vector E1, E2, and so on, T, En. So I'll sketch an example in parallel. So it will be clear. So here is the example that goes in parallel. T is going to be from R4 to R3, defined by T of X, Y, Z, W is X plus Y, Y plus Z, Z plus W. Right. This is the, and you can verify it's a linear transformation. Alternatively, from now on, if you want to show that something is a linear transformation, you can just find a matrix, and if it acts the same as matrix multiplication, this serves as a proof that it's a linear transformation. So in this case, the matrix A is going to be the following. So what is T of E1? E1 is 1, 0, 0, 0. What is T of E1? 1, 0, 0. And what is T of E2? 0, 1. Just the Y is 1, and all the others are 0. So it's 1, 1, 0. And T of E3, no, not N. T of E3 is, everything is 0 but the Z. So it's 0, 1, 1. And T of E4 is 0, 0, 1, because only the W is 1 and the rest are 0. So this is going to be the matrix A. I don't explain you, now I'll explain why it works. Yeah, it's like landed it from the moon, but this is something that works. I want to find the matrix. This is something that works. Later on, we'll see what is this the only one that works. I'll show you also uniqueness, right? I have to show you uniqueness. So if this works, I'm going to show you this is the only one that works. So this is the way A is built column-wise. Okay? Now we want to show that T is TA. To show, first of all, we want to say that A is in the right place. Where A should be? In matrices M by N. So indeed, A is in M by N R, since it has N columns. What determines the number of columns? No, not number of transformations. What establishes the column? Yeah, the dimension of the space V. The number n, it has n columns as the number of elements in the standard basis of Rn, as the number of elements in the standard basis of Rn, and why m rows, and m rows, since TEI, where is TEI? Is in Rm. Since TEI for all I is in Rm, and this is column of the matrix. Here it's obvious.
Could you repeat הגדרה?
Definition of what?
Definition of TEI?
Just you have a linear transformation, and it just remember T is a function. T is a function, and this is like doing. This will be clearer. T like f of x. It's like putting the argument in the function, but we don't use the parentheses because it's too much parentheses to write. So TEI is the vector in W where T sends EI. T is a function. It sends vectors from V to W. TV, TV is just writing T of V, right?
Not a new thing, TEI?
Yeah, TI is a vector in...
Already defined?
because if you know what is T, you know what is TV to all V. So, you know. So here, and indeed, you see there are 4 columns, because this is R4, and 3 rows, because the result is in R3. Okay? This is something to remember. It's important. If the transformation is from Rn to Rm, so the corresponding matrix is M by N. It's flipped, okay? It just takes a few moments to recall it, but this is something very useful to remember. Right. Okay, now what we need to show, the main thing, that this is a good matrix for our purpose, right? That indeed T equals TA. Where I'm going to write it? Here. Okay. To show that T equals TA, one needs to show that for any V in Rn, TV equals AV, right? This is TV, and this is TAV. Okay. TV equals TA of V. We want to show that this transformation is the same as this transformation, so we want to show that it's identical on all vectors, and this is AV. Okay? So this has to be done for all vectors in Rn. So take one. Take V in Rn. So let's write V is some A1, A2, all the way to AN, right? So first of all, let's calculate the left-hand side. What is TV? TV is T of this vector. Okay, but first of all, let's see what it means. It means that, as I remind you that writing an element in Rn this way is like writing the coefficients, the coordinates relative to the standard basis. What is V? That V is A1, E1 plus A2, E2, and so on till AN, EN, right? E1 is just the first element, and E2, the coefficient is the second element, and so on. So, T V is T of A1, E1, and so on to AN, EN, right? And by linearity, it's A1 TE1 plus A2 TE2, and so on to till AN TEN. As I told you last time, if you know where T sends some basis of V, you know where T sends everyone. In particular, if you know what is T, you know where T sends the standard basis. Therefore, only by TE1, TE2, and TEN, and all the way to TEN, you know where does T sends any given vector. So this is TV. Now we want to show that this is exactly what happens when you multiply AV. Okay? So leave A is here. Now let's calculate AV. AV. So A is this matrix. AV is this matrix multiplied by V. A1, A2 to AN. Yeah.
Can you explain the last step in the center panel?
This?
Why did you fill out the A's?
Ah, because T is linear transformation. So this is the mean. It respects linear combinations. T of a linear combination is a linear combination of T's. That's the thing. It happens only to linear transformations. Otherwise, we can't do it. Am I still heard in the speakers? Or not anymore? What? I'm still here? Yeah. Great. Okay, something with the battery. Okay, so now let's calculate AV. AV is the matrix A as we defined it, multiplied by V. So, which rule or notion about matrix multiplication we can apply here? Right. So when you multiply A by V, the result is, one way to view it, is the linear combination of the columns with coefficients of from the vector V. Okay? So recall that the result, the multiplication AV is a linear combination of the columns of A with coefficients from the vector V. So what we get here? We get here A1 TE1 plus A2 TE2, and so on till AN TEN. And this is equal to TV. That's all. Now, okay, first of all, is this clear? Okay. Now, for uniqueness, why this is the only matrix that works? Is it possible that there is some other matrix B such that T is TA and also T is TB? So, to show that A is unique, we will assume that there is a matrix B such that T equals TB. T is a multiplication by B, and we will prove that necessarily B is none other than A. Okay, so we assume that there is a matrix B, that T equals TB. We know already that there is at least one such matrix, the matrix A. So it's not a very crazy idea to assume that T is equal to matrix multiplication. So how do we prove that B equals A? Again, let's prove it column-wise. If T equals TB, then T for all I from 1 to n, TEI equals TBEI. Right? The same transformation. It has to do the same thing to the same vectors. TEI equals TBEI. And what is TBEI? Is BEI, right? But what happens when you multiply a matrix by a vector from the standard basis? What is the result? No, not the matrix itself. It's a column vector you're going to get. But which column vector? The ith column from B. Note that BEI is the ith column of B. So the ith column of B must be TEI. But this is how we define the ith column of A. Exactly the same as the ith column of A. Hence, B equals A. Right? Okay. This is uniqueness. In other way, there's only one way to represent T by a matrix. Now, let's say go for the example. So this is the matrix, and now we want to show that so TV we already have written explicitly. Now let's see what is AV, right? So AV for a general vector, A of x, y, z, is multiplying x, y, z by this matrix. So what do we get? X plus y plus z. We apply it on a, oh no, this is from R4. We apply it on the vector x, y, z, w. X plus y plus z, and z plus w. This is exactly as T of x, T of TV. Exactly like TV. Okay, so let's denote this special matrix that corresponds to the linear transformation T with a special notation. This matrix is denoted by T of B. Okay. So now I don't explain this E, but later on it will be more clearer. Okay. Is everything clear till this point? Because we are now starting some other subsection about linear transformations. So if this hasn't been clear, you can rest with it for a moment and then it will rise again. But okay. So the kernel and the image of a linear transformation. Let's write it larger. What? Just a moment. So the kernel is גרעין, and the image, the תמונה. Okay. So let's start with the image. This is the easier part and the more general part. Everyone knows what is an image of a function? No? Okay. So generally, think of a function between two. This is the preliminary. You should know it. Think of a function between two sets, right? So this is the domain, and this is the range. But in the range, so what is the function? It just matches elements in A to elements in B, right? So some elements in B are indeed matched by F to someone from A, but some of them are left alone and no arrow goes inside them, right? So if we separate B to those who are indeed images of someone in A, so this set is the image of the function, and set has no name. So these are all the ones that are left alone and they're not matched by anyone from A.
Is there a name for the corresponding set in A?
What? No, no. The definition, by definition, a function has to match everyone in A. Okay. Right. The function, the domain of the function must be the entire A. The range, the image, is just a subset of the range. Right. So this is the range. This is where F goes to, but the image is just a subset of the range. So for linear transformations, the image is the image. It is nothing different than the general concept of an image of a function. Okay, there's nothing about the linearity of T that goes into the definition of the image, right? So image, this is how it's denoted. Image T is the set. Here, let T from V to W be a linear transformation. So the image of T are all the elements in W such that there exists someone in V that TV equals W. There exists V in V such that TV equals W. Another way to think about image T, more compact way, these are all the vectors of the form TV for some V in V. Right. Go through all the elements, now this is V and W, right? Go through all the elements in V and ask yourself who are the elements of the form TV for all the elements in V. So the collection of all these elements that can be represented as TV of some V in V, this is the image. Now, it's a subset of W, right? By definition. But in linear spaces, we are not interested in subsets. What are we interested in? Subspaces, right. So, indeed, image of T, and this is something unique for linear transformations, there's no notion of subspace if it's a general function. Image T, for linear transformation T, is a subspace of W. Image T is a subspace of W. So, how do we show this? We have to take two elements in image T we have to show that image T is closed under summation and linear and multiplication. If we take two elements in image T, two W's, W1 and W2, so W1 plus W2 has also to be in the image. And lambda W1 has also to be in the image. We have to find someone back in V that goes to that W1 plus W2 or lambda W1. It's fairly easy, okay? So if W1, W2 not in W, in image T, and lambda 1, let's do it, lambda in R, then, first of all, by definition, there exists V1 and V2 where? In V, such that, what does it mean that they are in the image? There exists someone in V such that TV equal W. So TV1 equal W1, TV2 equal W2. Now, so let's do it. How do we show that W1 plus W2 is an image T? We have to find someone in V such that T of that someone is W1 plus W2. Give me a guess of that someone. T of V1 plus V2 is TV1 plus TV2 is W1 plus W2. And T of lambda V1 is lambda TV1 is lambda W1. This shows, so hence, W1 plus W2 is an image T, and lambda W1 is an image T. This shows that image T is closed under summation and linear multiplication. It shows that image T is closed under the linear operations which linear operations? Of W. No, from W, that's the involved. All these summations are done in W of W. So it follows that it's a linear subspace of W.
You also have to show that W is the in T is not empty, right?
Ah, thank you. Indeed. Well, why is image T not empty?
Because there is V1 and V2.
Yeah, so, well, it's indeed rather redundant because V is not empty. Okay, this is the main thing. Since V is not empty, so there's someone in V, so T sends someone to someone in W. That's the main thing here. So since V is not empty, image T is not empty. Everything else follows from there. Okay, now for the kernel. The kernel is something that is uniquely defined for linear transformations, and as follows. So, ker T is the notation for the kernel of T. These are all the vectors in V. Okay, the image is a subspace of W. The kernel is, we'll soon show it's a subspace of V. All the vectors in V such that TV goes to 0. It will be of particular interest. Who are the vectors in V that T sends to the 0 vector of W? Huh? 0 vector.
So just remember before we proved that in T is a subspace of W.
In T is subspace of W. Okay. Now, ker T is obviously a subset of V by definition, is so here we have subset of V, and here we state that T is subspace of V. So if V1 and V2 are in T and lambda in R, then how do we show that V1 plus V2 is in T? What is the requirement? The T sends V1 plus V2 to the zero vector. Then T of V1 plus V2 is, by linearity, TV1 plus TV2 is 0 plus 0 is 0. And T of lambda V1 is lambda TV1 is lambda times the vector 0 is the vector 0. So these two facts, this shows that T is a subspace of V. Am I still heard in the speakers? Indeed. Okay. Don't believe the red light. Okay, so let's do an example. Oh, now I hear myself. Okay. Let's look at this example. No, let's do some other example. T, where is it? T of xy zw is x plus w over 2, y plus z over 2, 0. Okay, this is from R4 to R3. So what is the image of T, right? Image T. Yeah. I want to claim, okay, so let's see that the image of T are all the vectors of the form A, B, 0. So any vector of the form A, B, 0, I can reach by applying T to some vector in a... Okay. So this is a claim for the image T. No, I have to state it. It has to be a set. It's all the vectors A, B, 0, such that A, B in R. Okay, now it's clear. Now it's a good statement. I want to show it by inclusion from both parts. Every vector in image T is of that form. This is straightforward. And the other way around is that every vector of that form I can get, I can see it in image T as the image of some vector in R form. Okay. So the inclusion from left to right is clear. Denoting x plus w over 2 by A and y plus z over 2 by B. So every vector in the image is some A, B, 0. Okay, for the inclusion in the other way, is this clear? For the inclusion on the other way, take AB0 in R3. What do we have to show? That there is someone, at least one, vector in R4 that is sent by T to this vector. So, give me an example of such. There are many, in fact.
What are you asking for?
Okay, I want to show that this vector is in the image. What does it mean to be in the image? That there is someone in T is from R3 to R4, right? R4 to R3, sorry. I take a vector of this kind. Just a moment. I take a vector in this kind, of this type, this form. It's in R3. I want to show it's in the image. Just a moment. So I want to find someone in R4 that T sends exactly to the AB0. Adi, what you had to comment?
No,
You had a guess.
yeah.
Okay, so what is the guess?
Maybe we can do just like x plus w divided by 2 equals a, then x equals 2a divided by w.
What Oli said is indeed right. Take A, B, B, A. This is going to work. Right. So, no. Yeah, there are lots of things we can do. Note that T of A, B, B, A, this is someone in R4, so T works on it and sends it somewhere, is, by the definition of T, A plus A over 2, B plus B over 2, 0, this is A, B, 0. So, A, B, 0 is in image A, image T. This completes the proof that this completes the proof of the characterization of image T. This shows the characterization of image T is as stated.
All you have to show is that there is some vector that is included in image T.
No, this is not what I showed. I gave here a characterization that image T is identical to all the vectors of this form. In other words, any vector with 0 on the third position, on the third entry, is in image T. So, in order to show this inclusion, I showed this equality, I showed inclusion in two directions. Every vector in image T, indeed, the third element is 0. This is by definition. And now I take some general vector with third element 0, and I show it's in image T. I have to find one vector, one example of a vector in R4 that T of which is AB0. I took a specific one. Okay, I took specific vector AB0. But what is specific? Specific but general. I take AB0, but it can be any A and any B. So for any AB0, take this vector, and you see that it goes, this vector is sent to AB0, therefore AB0 is in. And this goes for all A's and B's. So the inclusion, every vector of this form is in the image. And the inclusion is in both, is two-sided, so there's equality. Right. Yeah.
About the marking, it's okay to write that this AB0, what you wrote there is equal to
Belong?
it's
Included?
Yeah, belong. It's the same as writing that the set AB0 for all AB in R is
Subset of,
yeah.
yeah. If AB0 is inside image T for all AB, so this set, I showed you that every element in this set is in this set. So this set is subset of this set. Okay, this is the definition of, yeah, okay, now what about the kernel? Let's give a claim for the kernel. So this is just solving an equation. Yeah, we have to find all the x, y, z, w such that this is 0. Okay, so let's not just give a guess. Let's solve it. Okay. Kernel T are all the x, y, z, w such that x plus w over 2 is 0 and y plus z over 2 is 0. So this is the rule. Every time you have to calculate a kernel, you'll in fact have to calculate some solution space of a linear system, of a homogeneous, obviously, linear system. So these are the solutions. These are the, oh, not this, this is the space of solutions to the system with the system. Let's say neglect the 2 there. X plus w equals 0, y plus z equals. This you don't have to solve by matrices. This is clear. But again, um, x x is minus w and y is minus z. So now we want to write the general solution, right? So it is so generally you will have to solve the linear system and find the space, the solution space. This is the following set. So x y minus y minus x such that x y in R. If I want to write it as a span of some vectors, span of which minimal set is this?
1, 0, 0, minus 1, plus 0, 1, minus 1, 0.
Not plus, and.
Yeah.
So instead of writing with x, y, and R, when you write span, it means x, y, and R combination. Okay. So just one last definition as notion. So in general, yeah, this is the end of the example. Now back to the general case. The dimension of ker T is called the nullity of the transformation. I remind you there was a nullity of a matrix. Nullity of matrix was the dimension of the null space. So there is a correspondence between ker T and the null space. They are connected. The dimension of ker T is the nullity of the transformation T. Yeah, n of T. No, we don't use it usually. What?
What does it mean?
The dimension of ker T, you understand what it is?
Yeah. What is the nullity of?
The nullity are absolute. Okay? The nullity of the transformation. Okay? The degree of this what it is. Okay? What is the, how big is the space that goes to the 0? Okay? So for instance, if you have the linear transformation from R2 to R4, but you have it's the zero transformation. So what is the nullity of T? No, the nullity is a number. It's a natural number. The nullity is the dimension. What is the dimension of what is the kernel of this transformation? Okay, the kernel are all the vectors in R2 that are sent to the zero vector.
R2.
Is R2. The kernel is R2. What is the dimension of the kernel?
2.
2. No, dimension of R2 is 2. Okay.
The kernel is R2,
T of R from R2 to R4, T of V is 0 for all V. For all V. So ker T is R2. And the dimension of ker T is 2.
why does KT is R2?
Because TV, T sends to 0 all the vectors in R2. So the kernel is R2. So the nullity is now the dimension of the image is the rank of the transformation. And just note that it corresponds exactly when we talk about transformations that are matrix multiplications. But we showed already that these are all the linear transformations between any two Rm spaces. Okay? So note that if T is some metric, is transformation that is represented by a matrix multiplication, right? Then ker T, how does it relate to something we know about A? Yeah, it's the null space of A.
Not TA.
What?
TA.
No, T is TA. So ker T
okay, yeah.
is the null space of A. And the image T, now that's the tricky part. What is it of A? So think about it. It's all the vectors of the form AV. It's all the vectors of AV, such as V in some Rm. Right. So when you multiply AV, I told you, you take the linear combination of the columns of A. So when you take AV for all V in Rn, you take all the linear combinations of the columns of A. This is the column space of A. Rn. Since this AV, when you take all vectors in Rn, are all the linear combinations of the columns of A. Okay, so here we stop, take a break, and return, and learn more.
הייתי בשיעור קודם, אז סליחה, בשיעור. כן, מה קורה? מה זה? כלומר, הוא התקשר אליי לפני כאילו, הוא קיבל את הרושם שהייתה לו הבחירה בין שני הדברים, והוא התקשר אליי לשאול מה דעתי, אז אני מאוד הלכתי בכיוון של בסדר. כאילו, אז זה כבר, אתה יודע, דעתי בלי קשר, אז אין בעיה, אם הוא התקשר אני אשמח להגיד לו. אבל מה, הוא שבוז כאילו? מה שאני חושב שבאופן נוח ומתאים כן. איך חוץ מזה? שבוע 12, וואו. זה רץ, ושנייה, אתה חוזר להתחיל לפני אמרת? זה עוד שנייה, זה עוד 3 חודשים, לא? קיצר בסדר, אל תדאג, אין בעיה. עוד פעם?
כי אי אפשר כאילו, חבל לי גם הזמן.
כן.
לא. תבוא חבר של אח הגדול. איך קוראים לה? תראי לגדול הורים. כן.
כן.
חברים ודודים. באמת?
כן.
כן. האמת היא שאני ציפיתי שאם יבחור משהו, הוא גם ידבר איתי כשהוא נמצא. לא, לא, זה ממש פשוט. אחרי שכל כך הרבה אנשים יכולים כל הזמן, הוא צריך לתת משפט כאילו.
וואו.
אין כזה דבר נגיד.
מה?
אין ברוטינה שתסתכל עליך.
באמת?
נראה לי.
בוא נבחון.
הוא עדיין לא ראיתי
מה?
משהו כמו כזה אצלו.
מה זה השטות הזאת?
לא רוצה לדבר איתו על דברים אחרים.
בעייתי, אה?
כי הוא לא יבחור, זה גם מפחיד, זה כאילו לא...
וואי וואי.
תגיד, אנחנו צריכים דור. לא, צריך לשלוח אימייל. זה יוצא אוזניות.
הבנתי.
אנחנו כבר זמן עולם עכשיו.
לא, ברור.
ממש מאוד.
למרות שתחשוב שנעמה לימדה שם
ששנייה.
כמה שבועות.
חווה, כן, לגמרי יום. האמת היא שעכשיו זה בעצם
יש.
אתמול ישבתי בסדר, פשוט אמרתי, ממש בא לי
לא, לא, עדיף שם, אנשים
לא אוכל,
יחנקו.
כאילו, לא לגעת בכלום, ופשוט לישון בדברים שבא לי לעשות. ולא להיות לבד.
בכלל רציתי לומר שיהיה לנו כזה שקט.
לא, יש דברים שאני רוצה, יש תערוכות רוצה לראות, משהו רואה את
רציתי
הדמות
לשבת
שלהם.
ולבנות על קיר. שמישהו יבוא ויעשה לי כביסה. להכין אוכל,
אוקיי, זה
בבית,
משהו באמת.
יעשה לי שיעורים ואז כבר נהיה...
כן. האמת שהתקשר אליי
Um, okay, and now the most exciting part, as I promised.
Can I ask a question about the last part?
Yeah, sure.
What was the dimension of the image?
What is the dimension of the image?
From the example we just
In the example, okay. So let's recall what was the image. The image was all the vectors of the form A, B, 0, such that A, B in R, right? So what is the dimension of this set? Is 2. Or if I ask you to write it as a span of some minimal set, 1, 0, 0, and 0, 1, 0. Okay, so it's 2. And now, okay, I remind you what we said about matrices, how all these numbers relate to each other. Remember? So n, let's go back there. N, the number of columns, sorry, n, the number of columns. What did we say it is?
NA plus RA.
Is the is NA. NA is the nullity, is the dimension of the null space, plus RA is the rank, the dimension of RA. Okay, so this is the dimension of NA, and this is the dimension of R, of the column space. Right? So now think of a linear transformation to what is going to correspond. The nullity corresponds to the dimension of the kernel. Exactly. The nullity is the dimension of the kernel. The rank is the dimension of the image. And where n, what n plays the role of what? So think again about transformations which are represented by a matrix. A is a m by n matrix, where n is the dimension of the domain, right? If it's from Rn to Rm, so the matrix is n by m. So if it's from Rm to Rn, again, if it's from Rn to Rm, yeah. If it's from Rn to Rm, then the representing matrix is m by n. So n is the number of columns of the matrix, and it is the dimension of the domain. So now let's write the general dimension theorem for, linear transformations. The dimension theorem for linear transformations. Okay, so the T from V W a linear transformation, then the dimension of V is equal to the dimension of ker T as the dimension of image T.
Are we going to prove this rigorously, or?
Yeah, you're going to prove it. But again, you have the hope, the understanding of where did you see this already. You saw it already for matrices. You saw already for matrices that n is the nullity plus the rank. And if the transformation T is such a transformation that has a representing matrix, so this indeed corresponds to everything about the matrix. The matrix is m by n. N is the number of columns, which is exactly the dimension of the domain, like the dimension of V, right? And so this is n. And the nullity is the dimension of the ker of T, and the kernel of T, and the kernel of this transformation is indeed the null space of the matrix. The dimension, the kernel of this transformation is the null space of this matrix, and the rank of the matrix, right, is the dimension of the column space, and it is the image. So we already, in a way, know this for transformations which have a representing matrix. What? Not all transformations. We proved the fact, the existence of a representation by a matrix only for transformations of this type, from Rn to Rm. If it's a transformation from polynomials to matrices, what would be a representing matrix? You can't take a matrix and multiply it by a polynomial and get them. Well, but this is something else. We'll discuss it next time. Indeed, there is something about what you say, but for now we only shown that there are representing matrices for transformations of this type, because we want the matrix to multiply the vector itself. But if it's a transformation from polynomials to matrices, so apparently you can't have a matrix, because you can't matrix multiplied by a polynomial gives you, I don't know what. Okay. So now let's prove it in detail. Okay. So take a basis V1 to Vm of ker T. Okay. So ker T is a subspace of V, and we just take a basis for that subspace. A basis, so all these Vi's from 1 to m are going to the, by T sends them to the 0 vector, and it's a basis. They are linearly independent, and they are spanning ker T. So this means, yeah, this means that we denote by m the dimension of, maybe I should have stated it differently, okay? Just a moment. What? The microphone is off. So let's see if it's because let's give it another time. Thanks. Okay, so let's add here something. Okay, so denote n the dimension of V, m the dimension of ker T, and we need to show that the dimension of the image is n minus m, right? Okay. We need to show that dimension of image T is n minus m. Right? That's the claim. Now, take a basis of ker T. V1 to Vm of ker T. Okay? Now, no, recall, this is a independent set in V. Is it spanning? Well, it might be spanning if m equals n, right? But if m equals n, we are done. Because the kernel of T is of dimension n. So what does it mean? If the image of T, if the kernel of T is of dimension n,
Then any base of it has n vectors.
right? But the kernel is of dimension n, and the linear space is of dimension n. So this is the zero. This must be the zero transformation, and we are done. Because what is the image of the zero transformation? Is zero. And what is the dimension of the zero space? Zero. So this is true. So if m if m equals n, it means that the basis for the kernel has n vectors, so it's n linearly independent vectors in V, so the kernel is equal to V. It means that kernel T equals V, which means that T is the zero transformation. Now the image then, image T, image of the zero transformation is the zero space, and the dimension of the zero space is zero. So the equation holds, the equality holds. So in this case, the dimension equality holds. This is one special case where to take a different argument.
Why is that the dimensions are equal, means that they are equal ker T is equal
Okay, so take a basis of ker T. You have n, the dimension of V is n. But if you take basis of ker T, you have in ker T n vectors which are linearly independent. But any set of n vectors which are linearly independent in V are a basis of V. So a basis of ker T is in fact a basis of V. In a linear space with dimension n, if you have n vectors which are linearly independent, they are a basis.
Yes.
Remember, it's any two of the three.
The spaces are if they have
This is a subspace of ker T is a subspace of V, right? So if you have a basis of size n for ker T, and it's a subspace of V, which is n-dimensional, so the basis of ker T is in fact the basis of V. Okay, but now what happens if m is less than n? That's the more interesting part. Do we need this? Yes, we need this. Here, this in front. Okay. So if m is less than n,
more than
if m is smaller than n. So what are V1 to Vm is a set, is an independent set in V. But it's not of the dimensions. The size of it is smaller than the dimension. So what do we know we can do? one vector and maintain linear independence. And if it's still smaller than n, we can add another vector. We can expand it by adding n minus m vectors to form what eventually? A basis of V. Yes. If we take this and we add another vector, and all the time we maintain linear independence and eventually reach V1 to Vn, a linearly independent set. So what we've done is we expanded this set to form a basis of V. Right? We can add n minus m vectors V m plus 1 to Vn to establish so that V1, Vn, Vm plus 1, Vn would be linearly independent and therefore a basis of V. Alright, this is something you've already done. You took a small set and you expanded it to form a basis of the linear space you are working inside. So now, how would we want to show, again, what our goal is, to show that the dimension of image T is n minus m. So how can we show the dimension of image T? We show that it has a basis with n minus m vectors. Give me a guess what would be a basis of the in T.
Could you repeat the
Those vectors
question?
that we added?
What?
Yeah, the vector.
What is it?
Wait. Too many questions. Just a moment. What was your comment?
Repeat the question.
Repeat the question. Your comment?
Repeat
Okay. Just a moment. Okay, I remind you, our goal is to show the dimension of image T is n minus m. So one way to show the dimension of a linear space is such and such is to provide a basis with that number of vectors to that space. So what we're going to do, we're going to show that there is a basis of image T that contains n minus m vectors. So now, the question is, what do you think we can use to form a basis of image T?
What are the vectors you added?
But the vectors added are in V, and image T is a subspace of W.
T of the...
Yeah, if I take T of these vectors, the claim will be that Vm plus 1, Vm plus 2, and so on till Tvn is the basis of image T. And so that T Vm plus 1, Tvm plus 2, and so on, Tvn is a basis of image T. This will prove that the dimension of image T is n minus m, as we want. Okay, so this is the strategy. We took some n minus m vectors, okay? So we have to show two things. That these are linearly independent, and that it's a spanning set of image T.
It's linear independent by definition. That's how we
Ah.
expand.
No, okay, so now a remark, important remark. If I take vectors which are linearly independent in V, and I go to T of these vectors, I go from this linearly independent vector to these vectors. Are they necessarily linearly independent? Does T preserve linear independency? Why not?
Could be the zero transformation.
Okay, because on the same way, think of these m vectors. They are linearly independent. The T of them is always zero, is independent. So no, a linear transformation doesn't, in general, preserve linear independence. Okay? But it will happen that these particular vectors we've chosen are going to be kept linearly independent also after transformation, but not then, other vectors. Okay, so everyone is clear with the idea, with the strategy, with what we are going to show? So first of all, linear independence. Okay. So T V m plus 1 to T V n are linearly independent. So what do we have to show? Assume we have a linear combination of them which is 0. Assume alpha 1 T, let's call it m plus 1, alpha m plus 1 TV m plus 1, and alpha m plus 2 TV m plus 2, and so on till alpha n tvn is 0. So by linearity of T, we know that this vector, alpha m plus 1 v m plus 1 alpha m plus 2 v m plus 2 and so on till alpha n vn is 0. So this vector, where it is, it's in V, but more particularly, where in V it resides? In ker T. Of course it's in V, but in particular it's in ker T. This in ker T. So if it's a if it's a vector in ker T, so we can represent it as the linear combination of the basis of ker T, right? Again, I've taken these vectors, I want to show about them that they are linearly independent. I take a linear combination of them that equals 0. I want to get eventually to the conclusion that all the coefficients must be 0. So now I go back to V, I find a vector, some linear combination of these vectors, which is in the kernel. So this is the vector in the kernel. I have a basis for the kernel. I erase it, but recall, V1 to Vm, this V1 to Vn, is the first m vectors we started with, are a basis for the kernel. So if this is in the kernel, I can write it as a linear combination of these vectors. Okay? So we can express this kernel vector. This is not a good term. There's no kernel vector. This vector, which is in the, you can express this vector as a linear combination of the vectors of the basis of ker T. So these vectors, alpha m plus 1, v m plus 1, and so on and so forth till alpha n vn is some beta 1 v1 plus beta 2 v2 and so on and so forth to beta n m vm. Right? So what's going to be the next step? Okay, but we aim for the conclusion that all these alphas are zero. How will we reach this conclusion?
Okay.
Of course, it's nothing, everything we done is good. But how do we get the conclusion that all the alphas are zero? So if we just switch this to the other side, get all these alphas minus all these betas, is going to be equal 0. And this will be a linear combination of what?
The vectors in K.
No, it's also the Vm plus 1 and Vn and the V1 to Vn. It is remember that the V1 to Vn is the basis of V. So this will be a linear combination of the vectors in the basis of V that equals 0. So what can you say about the coefficients? All zeros. In particular, all the alphas are zeros. Okay? So switch sides to get minus beta 1 V1 minus beta 2 V2 and so on, minus beta m Vm plus alpha m plus 1 Vm plus 1 and so on, alpha n Vn equals 0. So we call that V1 Vm Vm plus 1 all the way to Vn is a basis of V. So all coefficients, in particular all the alphas, must be 0. So all the coefficients are 0. In particular, alpha m plus 1 equal alpha m plus 2 and so on equal alpha n all equal 0. This shows that this linear combination must be a trivial linear combination and the TVI's are linearly independent. It shows TVm plus 1 all the way to TVm, TVn is a linearly independent set. Is it clear? Or was it too going forward and backward between the spaces? Okay. Now, okay.
I didn't understand this part.
Right. So till here it's clear?
Yes.
Yeah, we found the vector in the kernel. We can express it as a linear combination of the base of the kernel. Just switch sides. So take all the betas to the other way, other side, and you get this linear combination, which is 0. Now recall, it's not that we just took V1 to Vm, a basis of the kernel. We added vectors so that V1 to Vn is the basis of V. So this V1 to Vn is the basis. They are linearly independent. So if you have a linear combination of them, which is 0, all the coefficients must be 0. That's because linear independency of all the sets. This is linearly independent, but also all the set is linearly independent.
But why you didn't say that there?
Here,
Yeah.
this is not a linear combination of the V1 of the V's. This is a linear combination of the TV's. Right? This I don't know about yet that they are linearly independent. That's what I have to prove. And the fact that this one goes to 0, so fine, one goes to 0, the other two go to 0. Only after all these arguments, I get to the fact that these coefficients must be 0, or the alphas must be 0, therefore this is any linear combination that equals 0 must be done by trivial coefficients, therefore the set is linearly independent. Okay. Okay, now for the fact that it is spans. Okay, so I want to take one vector in the image, and I want to show that I can express it as the linear combination of these vectors. Only these small, only this set of vectors. Okay, so TV1 to TVM plus 1 all the way to TVM is spanning image T. So take W in image T. Okay, what can we say about W? Eventually we want to express W as a linear combination of these vectors. Yeah, but for start, we don't know anything about W, but what we do know, it's in image T. The only thing we can say is that there is a vector V in V such that TV equals W. So there exists this vector V in V such that TV equal W. Okay. So this is a vector in V, and we have a basis of V. This large basis. There's the M and the N size of basis. So express V as a linear combination of the given, it's not given, we took it, yeah, but of the basis of V we have at hand. The one we have established. Okay, so V is some linear combination, alpha 1 V1 plus alpha 2 V2 and so on, but I want to separate it to alpha M Vm plus alpha M plus 1 Vm plus 1 and so on, alpha N Vn. Right? We can express V as a linear combination of the bases. So W is T of V, is T of this linear combination. Now, W is TV. Instead of V, I'm writing this linear combination. Alpha 1 V1, so on, alpha M Vm, alpha M plus 1 Vm plus 1, and so on, alpha N Vm. What next? By linearity, I guess at least some of you see where it goes to. By linearity of T, this is equal alpha 1 TV1, alpha 2 TV2, and so on, alpha M TVM, alpha M plus 1 TVM plus 1, and so on, alpha N TVM. Right? And now, again, now we've expressed W as a linear combination of all these vectors. But we want to express W as a linear combination of just these vectors. But what can we say?
All alpha until m minus 1 will be 0.
Till m. All these V1 to Vm is the basis of the kernel. Each of them in particular is in the kernel. So TVI is 0. VI, wait, so VI to VM is in particular a subspace of the kernel. It's the base of the kernel, it's a subspace of the kernel. Each of them is in the kernel. So TVI equals 0 for all I from 1 to m. So this is 0. So this is 0. So what we are left with? We're left with this linear combination.
We know this also because we showed that right? We showed that.
No, it's not, nothing here is because they are independent. So this is, what we are left with is alpha m plus 1 t v m plus 1 and so on. And let's write alpha m plus 2 to be nice, more clear. Alpha m plus 2 t v m plus 2 and so on. Alpha n t v m. Okay, now again, observe the beginning, the start point, and the end point. We started with a W, which is in image T. And after some arguments, we've managed to show the W is the linear combination of these vectors, T, V, m plus 1, these vectors. So any vector in image T is the linear combination of these vectors. This is the spanning set. It shows T, V, m plus 1 to T, V, n spans image T. And now, since it's a spanning set and linearly independent set, it's the basis of image T. So you erase the dimension theorem, but I remind you that the goal was to show the dimension of image T is n minus n. Okay, so I just write it down. So dimension of image T is n minus n. I have an n minus n size basis for image T. Okay, and this completes the proof. So now, just an example, and with this we conclude. Um, so T of x, y, z, w, and T from R5, yes, is going to be x plus t over 2, y plus w over 2, and z. T from R5 to R3. It's not very different than what we've shown earlier, so we can calculate. No, we don't have the time. I'll just give you the kerr T is a span of kerr T. You just solve this linear system, this homogeneous linear system. This equals 0, this equals 0, this equals 0, and find the basis. So it's span of -1, 0, 0, 0, 1, and
T is 2. Yeah.
What about Z?
Yeah.
What about Z?
Isn't it supposed to
Yeah,
be
Z
0,
must
0,
be
1,
0.
0, 0, 0?
No, no, Z must be 0 in particular, right?
Okay.
Because if you want someone in the kernel, then Z must be 0. Yeah, don't confuse. 0, 0, 1 is in the image. 0, 0, 1 is in the image. But now, the image you don't have to calculate. That's what is nice, that you can conclude it from the dimension theorem. So, by the dimension theorem, dim R5 is dim ker T plus dim in T. Right? So what do we have here? We have 5. What's the dimension of ker T? Is 2 plus dim in T. So dimension of in T must be 3. So can you tell me what is in T? In T is a subspace of R3 with dimension 3.
The same scarcity, just with the one that's always...
No, what do you mean same as ker T? The image T is a subspace of R3. Can't be in any way the same. So image T is a subspace of R3 of dimension 3. So it must be R3 with no calculation. In T,
No mass center. Oh, okay.
in T is a subspace of R3 with dimension 3. So it is necessarily image T equal R3. Okay? So, with this we conclude today's lecture. And continue next time.
I don't give over too much. When I have to get up there,
Whose is this? This is not mine. Who gave it to me? Is it here?
oh, it's still Tuesday.
מה?
And next Wednesday.
כן. סליחה. מה, שאלות או מה?
Class.
מה נדבר? אתה נשאל אותה, אוקיי, אין בעיה. אני אפילו יותר משתי דקות, אני מחכה חלב. רגע, לא קצת זה שלה?
Yeah, I'm sure. She's gonna give birth any second, so she's exhausted.
Okay.
I really want to get a dinner with Pastor Connor.
Okay. So,
So,
an email will be sent. Did you get an email already?
Yeah.
So, contact me by mail.
Okay.
Okay.
I'm just telling you in person.
Yeah,
I
okay.
really want to get a dinner.
So, you're
תגיד לי אם זה שם X. ברור. יש את השאלות?
לא.
אין לך.
יש לי את הפתרונות.
לא,
שאני יכולה פשוט למסור לך את
לא,
הפתרונות.
זה לא ככה. תדע.
לא.
אז אני אכתוב את זה כי זה מאוד תלוי העתקה.
אני יכולה להעתיק מהדף הזה.
כן, אבל זה לא מספיק
לא
ברור.
ברור?
אם אני כבר כותב את זה, אני אכתוב את זה מחדש. אז צריך למסור, זו שאלה מספר 6.
אתה בטוח שזה לא כתוב על הלוח שהזלתם?
לא, זה היה כתוב, זה היה הלוח. זה היה הלוח.
אין בעיה, תכתוב מחדש.
אין בעיה. רק כמו שאמרתי, להקפיד על העתקה, כי כל טעות בהעתקה משמעותית. לא, פשוט שמעתי את התוצאות באופן משמעותי. אני נוטה לבדוק ביחס לטעויות העתקה, אבל אני לא רוצה, כי זה מסובך. אז יש לך שני מרחבים, והצלחה של x בשלישית ועוד 4x בריבוע ועוד 6. הוקטור השני זה x בשלישית ועוד 2x בריבוע מינוס x ועוד 5. השלישי זה 2x בשלישית ועוד 2x בריבוע פחות 3x ועוד 9. זה u, ספן של השלושה האלה. v זה ספן x בשלישית ועוד 4x בריבוע מינוס x ועוד 3. x בשלישית ועוד 5x בריבוע ועוד 5. 3x בשלישית ועוד 10x בריבוע מינוס 5x ועוד 5. ואוקיי, למצוא
עסקתי עם זה המון שעות.
אוקיי, למצוא בסיסים, לא לשלושתם, ל-u ול-u חיתוך v. ומותר לך בדרך למצוא בסיס ל-v, אבל אני מרגיש שזה מקצר.